Good afternoon. I'm Bob Miller, and I'm the Director of IVC Technology's Advanced Testing Group. And for this afternoon's webinar, the topic is going to be vibration analysis, starting off on the right foot. I've been involved in testing, diagnostics, machinery maintenance activities, and specifically vibration analysis for nearly 30 years now. And in all that time, I've seen so many tests that have gone south before they ever really got started. Big reason was people weren't taking the right things into consideration. They weren't doing the correct test plans. They weren't really thinking about the tasks that they had to conduct out in the field before they actually got there. So they pretty much shot themselves in the foot before they ever got started. The purpose of this presentation is to address those things that are important for you to think about, take into consideration, and really factor into your test plan before you ever get to the point where you actually press the button and start taking data. And with that, we'll go ahead and get started. To begin with, why vibration analysis? Why are we going to do this in the first place? I was lucky enough to work with a gentleman, Art Crawford. Unfortunately, he passed away last year, but he was one of the foremost guys in vibration analysis. He was really one of the pioneers, particularly when it came to rotating machinery diagnostics. I was lucky enough to know him as not only a friend, but a mentor, and also a peer. Probably one of the smartest guys that I know when it comes to vibration analysis. And Art said, of all the parameters that can be measured in industry today, none contain as much information as the vibration signature. In all my years of testing, I've found this to really be true. The biggest reason, regardless of what happens in process or production, if anything changes, typically the vibration signature reflects that. If temperature changes, the vibe signature will change. If the product that you're running changes, again, vibration signature will probably change. Even if you change something as simple as the operators, there can even be a change in the vibration signature. So it's an excellent telltale as far as, is my condition the same as it was yesterday? Are things running smooth and running constant? Or has there been a change, and particularly has there been a detrimental change that's something I need to pay attention to? So that's why we're looking at vibration analysis in the first place. Okay, why is this stuff important in the first place? And along with that, what's this garbage in, garbage out? Well, vibration analysis is a data-driven technology. So probably the most important thing is that I acquire good data. If I don't have good data, then everything that I'm going to be analyzing and making conclusions off of is going to end up being garbage. Hence, garbage in, garbage out. That's why so much of this stuff is important. You have to make the plans and take the precautions up front to make sure at the end of this whole thing that my deliverable is going to be a solid report, solid conclusions, because nobody can afford to waste time and chase their tail, waste precious maintenance dollars and operation or production time. So we don't want to get garbage in, and we certainly don't want to provide garbage out. If you're a consultant like myself, that's probably going to be the last test that you work on. So what's the goal? This is also important. You have to kind of know what my goal is so I can go about achieving it. If you don't have a clear understanding of a goal, how can you ever hope to achieve it? When you say, I want to measure vibration, what type of vibration exactly is it that you want to measure? Are you looking at measuring overall or trend data? Do you want to get detailed data like spectrum or time waveform? Those may require additional types of instruments or specific type of instruments. Are you looking at measuring baseline or commissioning or post-repair data? Are you doing diagnostics, and that can fall into both the simple category or advanced? Or are you testing to satisfy a standard or a specification? Those can also have some specific requirements for that test that may be defined by the OEM. All of these things come into play when you're figuring out what you need to do before you actually get to the part of doing it. Here's a simple example of some basic trend analysis where we can see before repair levels, and then you can see the trend drop to after repair levels. It's a very friendly plotting format and requires minimal information. It can be done with simple instrumentation. If we get to the next type, here we're looking at spectral data. where you actually have discrete frequencies. Again, it's very clear the before and after levels change drastically. When you start looking at spectrum analysis, this is where you figure out what are the specific frequencies that I'm going to look for specific problems like unbalance, misalignment, my gearing frequencies, my bearing frequencies. If I want to tell not only has it gotten better or worse, but it's gotten worse and the source is this, then I have to look at discrete frequencies in spectrum analysis. And I can't get that type of data with an overall meter. This is time domain analysis. This is actually the raw signal coming straight off your accelerometer or velocity probe or whatever you're using for your test. Again, it's pretty clear to see this is the levels in the before. These are the levels in the after, so I can tell there's been a drastic change. One important thing with time domain analysis, this is also very useful to figure out whether or not I may have an instrumentation or a sensor issue. First place I'll look for that is in the time domain to figure out, am I in fact getting good data? If I'm going to have to do testing on, say, turbines or very large slow speed pieces of machinery, essentially things that have sleeve bearings in them, then I'm probably going to be looking at using prox probes, and for the analysis method I'm probably going to be looking at orbit analysis. Again, this is one of the things that you need to take into account up front before you ever get to the point of actually doing the testing itself. A lot of the testing that I'm personally involved in is on rolling mills and other complex pieces of machinery where it's very important for me to not only know the frequency, but how those frequencies are changing and reacting through time when there are changes in speed, changes in product. As you can see in this plot, we took, in this case, a leveler, and we ran it through a series of incremental speed increases to use the system itself to map out the sensitivity, figure out where the natural frequencies were in the system, and figure out what the major sources were and if they were interacting with some of those natural frequencies that would then result in a quality issue. For this type of testing, I knew I needed to do time frequency analysis, which requires me to stream in continuous data across all channels through the duration of whatever period I want to observe. Another type of testing you may get involved in is either modal or operating deflection shape analysis, or ODS for short. In this case, it's where you want to actually make a picture and be able to see the shape of the vibration. A lot of times a picture is worth 1,000 words. Here you've got a typical roll stack, and you can see where the work rolls on the drive side are actually scissoring together. So if I'm running product through this mill, it's going to pinch the product at a periodic frequency that then equates to a quality defect. Again, it's another type of test, but it's something I have to take into account up front before I ever get to the point of hitting the go button to record data. Okay, the next step, how do we get there? By failing to prepare, you're preparing to fail. Mr. Benjamin Franklin. Once you have a clear understanding of the goal, you can set about achieving it. No matter how simple the test, do you have a test plan? The simple act of jotting down even a basic plan will typically flesh out issues that would be missed otherwise. It's that simple practice or exercise of going through in your mind, what steps do I need to carry out while I'm there at the test site in the field acquiring data. It allows you to identify things that, hey, I need to have provisions for power, or I need to have a test table, or I'm going to have to do these precautions from a safety standpoint. You always want to come up with a test plan up front before you ever get to the field. One of the things that might be very important, what measurement positions are you going to have to accommodate? Considerations like transmissibility. Look for the shortest, most direct solid path for vibration energy from bearing to your sensor. Places you'd want to avoid: fan shrouds, uneven surfaces where your sensor might rock. Minimize multiple material transitions. a bunch of seams or a bunch of welds, things that get between the sensor that's taking the measurement and the source of the actual vibration that you're trying to measure. Accessibility. A lot of this stuff may be covered or guarded, so you're going to have to factor that in and know about it up front so you can even get in there to put the sensors down. Repeatability. If I'm planning for something that's going to be read monthly or quarterly, I want to make sure that the location for the sensor mounting is clearly marked and identifiable, so each subsequent guy that goes in there to take data can find the exact right place so my trends are accurate. This falls back to the garbage in, garbage out concept. Another important thing, measurement planes. Different measurement directions are going to determine what you see in terms of the vibration shape itself. Do I need to measure in the horizontal, which would be side to side, vertical, or even axial? Typically, if you're looking for things that generate a lot of thrust, like angular misalignment, the axial measurements are particularly important. You should note transducers are very directional and should be placed on line with the center line of the shaft if at all possible. Position numbering. Again, from a consistency standpoint, measurement positions are generally numbered starting from the power source, which would be position 1, then following the path of power. Each position is described further with a directional designation such as horizontal, vertical, or axial. Again, following from driver to driven. So each subsequent guy goes out in the field and knows where to start and where to finish, so all the data goes into the right places, the trends are accurate, the data is accurate. Again, garbage in, garbage out. None of this is real complex, but it's very important to factor in. Route mapping. This is a big one, particularly if you're doing walk-around measurements, periodic measurements. It's very important to have a route map. A lot of times the simple act of jotting down on paper to see your specific path that you're going to take, it may be more efficient on paper to take things in sequence 1, 2, 3, 4, 5, and yet when you get out to the field, I can't follow that specific path. I may have a whole series of pumps or motors that are all in line. It may be more convenient and more efficient for me to take one side of one machine, then switch over and take the other side of the adjacent machine, then walk around the aisle and toggle again. So my path, as I physically take the data, may be anything but in a nice clean sequence with respect to a single machine. But if I jot it down in paper, I can figure these things out before I ever get out there and hit the field. And it also makes it much clearer if someone who hasn't been there before has to follow your route map and try to figure out where to take the right locations and the right pieces of data. This is showing just a typical test layout for the type of thing that my group gets involved in. We may not only take vibration data, but tap into a lot of the control signals. So things like interstand tension, motor current, shape, footage, force, speed, as well as vibration or any number of other signals. A lot of these are control signals, so there are a lot of preparations and protections that have to be in place to make sure that when we plug in, we don't actually interrupt or take down operations. Again, it's a lot of planning and preparation up front to make sure when we get in there to test, we don't have any hitches and we get the data that we need. This is just showing you an example of the layout for a typical animation test, where a lot of preparation is taken up front, where I'll build the sketch before I ever get ready to do the test itself, so I can figure out, based on the drawing, where I physically need to mount sensors to get the measurements I need to be able to come up with a good animation or picture at the end of the test. Next step, do I have the right tools? Do you have the right data collector to gather the necessary information? We briefly touched on it earlier. If I'm going to make overall measurements, that's a simple thing. If I need to take spectrum or time data, that's another thing. It might require a different type of analyzer. If I need to acquire multi-channel data and stream it in, that may require a different analyzer, more complex setup again. So do I have what I need? Do I have the right sensors? Are they the right sensitivity? Do they have the right temperature rating? Any number of things. Do you have the necessary cabling and connectors? This is important. I've seen a lot of tests go south for want of another type of cable connector. Do you have spares? Because the equipment never fails, and anybody that's done testing knows that. I only have one TAC cable, and that one's busted. Do you have contingency instrumentation? This is another big thing, and we'll touch on it in just a minute. Here I wanted to take a quick look at accelerometers and go over, some of the advantages. They read acceleration. They're small in size, lightweight, fairly inexpensive. They cover a wide frequency range. Charge modes in particular can measure very high temperatures. And there's a lot of current research to improve the design. This is kind of the workhorse of vibration analysis. Some of the disadvantages, it reads acceleration, and that's if you want another unit like velocity or displacement. There can be a limited signal to noise ratio. They require outside power. High frequencies can swamp the actual internal sensing elements. And double integration is required to cross all vibration parameters, i.e. get from acceleration to displacement. When we get to velocity sensors, you may see them on occasion, not that frequently from my experience. Some of the advantages, they do read velocity. They're self-generating, so they don't need external power. They have an excellent signal-to-noise ratio, and they're very rugged. But some of the disadvantages, they're typically big and bulky. They have a limited frequency range, a limited temperature range. They can be affected by magnetic fields. The output varies with the measurement axis. So if it's designed to measure vertically, it needs to be in the vertical mounting orientation. If you turn it on its side, you won't get the appropriate vibration output. It's not going to be scaled anymore. It's not going to measure properly. And also, they're relatively expensive. Next on the list is non-contact eddy current probes, or prox probes. Some of the advantages, they read displacement, and that includes measuring static displacement. They measure relative motion between 2 points. They're extremely accurate for shaft movement. They're somewhat inexpensive, small, and also lightweight. Some of the disadvantages, again, it directly reads displacement. So if you want to look at acceleration, this isn't the best choice. It requires a stable datum plane, or stable mounting or fixturing is what they mean. It requires an external power supply. The output can be affected by the specific material. It's also limited at high frequency ranges. Normally this is for slow speed applications where you have a lot of movement at a low frequency. And it does require double differentiation to cross all the parameters to get from displacement back to acceleration. Next is torque sensors. On the rare occasion, you may look at torsional vibration issues. In that case, you're not going to be wanting to use accelerometers or velocity probes or prox probes typically. What you need in this case is actual torque measurements that's done with strain gauges that are mounted to the shaft, wireless telemetry, so you can actually measure the dynamic torque and then transmit that off from the shaft assembly over to your data acquisition. Again, it's a specialized test. You're not going to run into it that frequently, but if you're in a scenario where you're busting up couplings or chewing up gear teeth, it's a perfect scenario where you actually want to measure the torque. So it's something that you need to plan for and understand ahead of time and factor it into your test plan. Data acquisition. Again, do I have the right data acquisition that I need? You can have something simple like this little overall meter. In this case, this top right one is a digital transducer where all the electronics to record the vibration, digitize it, and send it over via USB to a computer is all in one clean package. If you're looking at something that would be for permanent mounting, online monitoring, you may be looking at some type of rack assembly where you can have a controller and then a series of different modules to measure vibration as well as process control parameters, pretty much anything under the sun. The analyzer shown here in the center is one that we've used frequently, specifically for crane testing, where we have to have a larger channel count. We can record up to 16 channels of vibration, and it's also battery powered and very portable, so we don't have to drag AC power supplies and those kind of things and extension cords to accomplish a multi-channel test. And then in the bottom right, this is your typical scalable, semi-luggable rack mount type data acquisition system where you can add additional modules and go from 8 to 16 to 56 to whatever your necessary channel count would be. Depending on what you need to accomplish the test, that's really what's going to determine what type of data acquisition that I need to bring with me. And then we had mentioned previously contingencies. Sometimes you may get out to the field and you're getting ready to do vibration testing and realize vibration isn't the parameter I should be looking for. It may be temperature, it may be ultrasonics. I may want to actually pull out a strobe light to freeze the shaft and see if I have the shaft oscillating or if it looks like the key is bouncing around in the keyway while it's turning. This is what I mean by having contingency plans. These are some handy things to plan on upfront just in case I need them to have with you. So it's always good, again, to plan ahead. So when I get out there in the field and I'm running the test or getting ready to run the test, I have everything that I need. The next step, certified versus qualified. Warren Buffett said risk comes from not knowing what you're doing. And it's absolutely true. One of the big questions, are you certified to perform the test? In some cases, this is absolutely critical, even though it won't be inherently obvious until after it's already hit the fan. Are you also qualified to perform the necessary test? Certification is one thing. I've passed a test. I successfully proved my level of knowledge for the task at hand, so they awarded me a certification. Being qualified means, okay, I've not only passed the test, but I'm comfortable, knowledgeable, and I'm capable of doing the test successfully. Two completely different things, and oftentimes they get confused, unfortunately. Just for example purposes, if you're Category 1, this is a listing of the requirements, and this comes from the Vibration Institute for their vibration analyst classifications. At Category 1, vibration analysts are qualified to perform a range of single-channel machinery, vibration, condition monitoring, and diagnostic activities, including data acquisition on predetermined routes, machine steady-state testing to predefined procedures, and comparison of readings against pre-established alert settings. Essentially, more senior analysts are setting things up, and your biggest responsibility is to go out and successfully acquire good data, but you're not defining anything, configuring anything, making any of the judgment calls. You can also see there's a minimum recommended experience of 6 months and minimum training hours of 30. Now when you get to Category 2 vibration analysts are qualified to perform basic vibration analysis using single-channel instruments according to established procedures, set up instruments, and maintain database of results. You're only getting your feet wet in the analysis portion, and you're still having a majority of the activities defined or established by more senior vibration personnel. Minimum recommended experience at this point is 18 months, and minimum training hours is 60 hours, which is inclusive of the 30 hours previously for your Category 1. It's like most trades where you're gradually building on training and experience like a skilled trade. When you get to Category 3 vibration analysts are the workhorses. They're qualified to establish, direct, and or perform programs for condition monitoring and diagnostics of machines, including spectral, waveform, and orbit analysis. Category 3 certified vibration analysts shall be qualified to perform minor corrective actions involving operating deflection shapes, single plane balancing, as well as diagnostic testing. The minimum recommended experience at this point is 36 months. The minimum training hours, again, now it's more. We're up to 90 hours. The last category is Category 4, and this is primarily where you're going to be dealing with people that are consultants or specialists in the field of vibration. Category 4 vibration analysts are individuals who understand the theory of mechanical vibrations, advanced vibration analysis techniques, and signal analysis. They shall be qualified to direct condition monitoring programs, perform major diagnostic efforts, and perform and recommend corrective actions, as well as design modifications. So this is the last level of certification. If a person is Cat 4, he should be able to handle just about anything in the realm of vibration analysis, which is also why you have recommended experience of 60 months or 5 years and minimum training of 130 hours. The next step, and this is an important one, mechanical info. Having accurate mechanical information eliminates guesswork in vibration analysis, and guesswork is not your friend. And like we talked about garbage in, garbage out, this is another important concept. Pay me now or pay me later. And later it's always more expensive. You're much better off by doing your homework, getting the mechanical information up front, so then when you get to the analysis phase, you already have all the prints, all the mechanical details, and don't have to spend the time when you don't have it trying to chase down all that critical information. This is just an example of some of the detailed info that you might be looking for, whether it's specifics on the bearings with the geometry so you can calculate the frequencies. If you're looking at gearbox drawings and trying to find out the specific number of teeth and what bearings are in the gearbox, be prepared to spend some time doing this, because much of this you're going to have to get it from the OEM, and the OEMs may consider some of this proprietary information. But typically, if you explain that you're doing vibration analysis and you're not trying to rebuild the gearbox, you'll find them very helpful and very friendly. A practical field example, I was involved in testing years back where we were actually testing on a different mill doing a torque test, but I knew the manager and he asked me to take a look at a winding reel gearbox that was making a lot of noise. We moved the equipment over, we took the data, put a tack on it and a series of vibration sensors, streamed it all in, and then the first thing we did was ask for the mechanical information, and he provided us prints that showed it had SKF bearings and 48 teeth meshing with 47 teeth. Well, once we started getting into the data, I know the ratio and I measured the input speed, so if I apply the ratio, I should be able to accurately calculate what the output speed is. And in this case, when I looked at the actual data using the reference, the numbers simply didn't match up. So instead of going by the numbers that were provided, one of the things you can do when you're more experienced is actually throw out the mechanical information, use the vibration to try to estimate and come up with what you think the gear mesh actually is, and possibly even what you think the bearing frequencies are. So we came up with estimates, we called them back and asked them to open up the gearbox and verify the numbers, actually count the teeth if possible, to make sure that we're not chasing the wrong frequencies. When we did that and followed up with them, it turns out that tooth counts were incorrect, our estimates were correct, and when we followed through with the rest of the numbers, we weren't actually dealing with gear problem per se. It was actually an inter-race fault that was in late stage failure. And here's a picture of that failure. So this was the actual problem, even though for 5 months prior to us being in the mill, they had been chasing or trying to evaluate a gear problem, and it wasn't a gear problem at all. It was a bearing problem, but it's because they didn't have the right mechanical information. Calibration. This is another important step that's often overlooked. Fast is fine, but accuracy is everything. Wyatt Earp. Is your data collector calibration current? This is something you need to know. Does it need to be for the required testing? Some of the testing that we mentioned earlier, baseline tests, commissioning tests, testing to an OEM standard, All of these may require that all of your data acquisition, including your sensors, have to be in cal. In fact, very often you may have to provide the calibration sheets along with your test data at the closure of the project. If your current calibration isn't required, what can you do to make sure that you're still getting good data? This is just a quick field test. If you have a known machine that never changes, it's very stable, you can compare last month's levels to this month's levels at that same position, and if everything looks the same as expected, then you're probably taking good data and you can rely on what you're acquiring. So you don't end up taking a batch of bad data, being unaware, and then getting back to the office only then to figure out that you've wasted the entire day. The price of low cost. Many, if not most, general-purpose industrial accelerometers come with a single-point calibration as opposed to checking the entire frequency range, even though a lot of people think they are checking the entire range. The nominal sensitivity can vary by as little as 5% and as much as 20%. A lot of this will also determine the cost of the sensor. The tighter the tolerance, the more you're going to pay. The stability of natural quartz piezoelectric crystals is much better than ceramic crystals, which have become the standard. There's a lot more control as far as the wide range of sensitivities with the ceramic, but again, they're much less stable, so if you drop the sensor, it's much more likely to get knocked out of calibration. And again, you're back to taking garbage data. This plot just shows you some of the potential error to give you a feel for that. The table on the left shows you essentially the range of sensitivity from a batch of 500 millivolt per G nominal sensitivity sensors, but they ranged from as high as 557 to as low as 498 millivolts per G, and all within spec. Now here you can take the nominal sensitivity and look at what plus or minus 20% actually results in. So if you're not tracking your specific sensor that you're using for your monthly measurements, you could get a significant jump in levels and write it up as an increase in vibration levels and call for an inspection. And it's just a change in the sensitivity of the sensor that you used for that specific acquisition. So it's important to keep track of and pay attention to this. In-Situ Calibration, where this comes into play is if I need to perform a complete end-to-end calibration, particularly for my online monitoring systems. I run into a lot of customers that have a monitoring system in place and they're not entirely comfortable or confident that they're getting accurate levels, accurate measurements, and that the system is actually doing what it needs to do. So the only way to absolutely verify this is to take a portable field shaker like shown here, take it out, mount the sensor down out in the field, and then power it up and feed a known signal all the way back through to your data acquisition. So in that scenario, I'm actually calibrating the entire system from sensor, cabling, junction boxes, data acquisition, and even acquisition software and display software to verify and validate that I am getting good data and that the levels are what they should be. Visual inspection, another important step. It's not what you look at that matters, it's what you see. Henry David Thoreau. Visual inspection is by far one of the most important aspects in being successful acquiring good vibration data. A good vibration analyst can often figure out a vast majority of the problems before taking the first set of data by simply paying attention. And I'll estimate that at probably 85% that you'll figure out before you ever have to take data set 1, if you're good. As a formal ASNT discipline, visual inspection is extremely complementary to vibration analysis. You shouldn't go out there in the field and just blindly take data. Pay attention to the machinery that you're around. Visual inspection. Here's some examples of things that you're supposed to be looking for. What's the condition of the bearings? Look at the motors. Look at the shims. The general cleanliness. You're also authorized and completely capable of using your other senses. Does it feel hot? Is the temperature abnormally high? Is there a lot of abnormal noise? Is there excessive movement that you can visually see? Is there an abnormal smell? A lot of times if there's an electrical issue or things are burning, you get that acrid scent. These are the things that you want to pay close attention to because they're going to have a significant effect on the vibration signature. And that's the whole purpose of this. How can I make sure I'm getting the most accurate information, the best vibration data, the best field notes, so I can come back and do a good analysis. Here's an example of a spindle. When it comes to visual inspection, one of the things that people don't realize when they're looking at tolerances, they may look at the individual tolerance and not put them together. It's important to note that it's the combined wear between the flats, the spade, and the radius inside the pod that determines whether the spindle pod runs true during operation or becomes misaligned and or flops. And here you can see the flopping, and we can actually play this wave where you'll be able to hear when this thing comes up to speed, it really starts flopping around. Okay, so that's not what a normal spindle coming up to speed is supposed to sound like. So again, it's not just one tolerance, it's the tolerance of the spade combined with the tolerance of the insert that it's fitting into that's out of specification. So it's just an area to pay attention to. Another important step, mounting method. Sensor mounting has the single biggest influence on vibration sensor frequency response, which is one of the most critical aspects when it comes to acquiring good vibration data. Then here you can see this is a standard plot where as you move from stud mount to adhesive mount, mounting pad, flat magnet, dual rail magnet down to hand probe, you're gradually losing more and more of your linear frequency range, which is the data that you're going to be using to do the analysis. This is just showing you some plots using your stud mount, which is your best case scenario. I'm linear probably out here to say 15K, almost 16K. Glue is actually pretty good. I can probably go out somewhere to 12K on this. But you'll see as we change the method, you'll gradually start losing more and more of the frequency range. Magnets are probably going to be the most popular mounting method. If you're using a flat rare earth magnet, even with that on a good mount, now you're down probably in the 8K range. And if I go to the big bipole magnet that's handy for putting on round surfaces, well, now I'm less than 4K as far as my linear range. These are some of the conditions that you're going to run into in the field. In this case, one of our guys is up on top of a crane, and a lot of this dust you can see floating around and piled up on top of the machinery is metallic in nature. So what does it do? It sticks to magnets. And if you're not very judicious about removing the iron fines that build up on the magnets, essentially this part ends up being a big metallic cushion, which further lowers the frequency response range for the sensor. And again, you end up basically taking garbage data. When that builds up, you're going to get this shift, which if it's a rare earth magnet, it's going to push it down. If it's a bipole magnet, it's going to push it down. So eventually you get down to the point where you're not even measuring in the range of all the components that you're trying to assess. So it's something to pay attention to. Lastly, stingers. I'm not a big fan of stingers, but there's some scenarios where that's the only thing you can use to get in and get a measurement. One thing to remember, the longer the stinger, the worse the frequency response. With a 2-inch stinger, you can look, you're maybe at a kilohertz, if that. Once I get to the 8-inch stinger, I really don't even have a linear range down here. So will it give me some indication of vibration that's occurring? Yes. Can I rely on the level? Absolutely not. So not the preferred sensor, but again, it's better than nothing, and if you're in a pinch, you have to use what you can use. This step, recognizing good versus bad data. Again, this is an important one. This is the single biggest reason that if you're taking vibration data, use a live display. So you can make sure you're taking good data and you're not out there wasting time. Because if you do end up taking bad data, you're probably going to have to go back and reacquire it again. These are just some quick examples of what you may see that's a flag for bad data. Anytime I see this big ski slope over here on the left-hand side, if I'm looking at the spectrum or the frequency data, that's an indicator. Also, if I'm looking at the raw time data and I see this slope across, normally accelerometers, acceleration, velocity data, it's supposed to be centered at 0 with some type of positive and negative signal. If I see this thing drifting down through the course of the data window, that's unsatisfactory. And even if you don't know what the source of the problem is, stop, quit taking data, and get someone that can help you resolve it. This is what it looks like if you're moving the transducer. Again, you can see where I've got some flat data and then the transducer was moving and the signal started floating around. This is an abnormal vibration signal, and the resulting data is going to give you garbage. Over here in the spectrum, again, you can see the ski slope on the left-hand side. That's an indicator for bad data. In the time domain, insufficient settling time. If guys get in a rush when they're taking route data and they slap down the magnet, that puts a huge transient through the electronics, and the electronics take a few seconds to settle out. If you start storing the data too soon, well, you're catching part of that settling period, which causes the data to drift across the window. If you're watching your data and you see this in the time data, simply reset the measurement, try it again, and it should stabilize out by the time you get ready to do the second acquisition. Sometimes you may run into bad hardware or software. If you see something like this where I go from lots of signal to an absolute flat line instantaneously, it's physically impossible. So again, you identify it as a problem. You may not know what the problem is, but at least you know enough to stop, get it resolved, get help, and then once you've got it resolved, go back to taking good data. This is just another example. Again, you can see this flat line that's in the midst of the data. It doesn't represent a real signal, and it's also not centered at 0, so there's definitely a problem. What it is, I don't know. It could be hardware, it could be software, but there's a problem, and the last thing I want to do is acquire more junk data. So I identify it, and I stop, and I get it resolved, or grab another analyzer that's working properly and pick up where I left off with the test. If you get overloaded sensors, if you're looking in the time data, this is going to be the signature for that, where you'll get an instantaneous jump, and nature of the electronics, it overloads the amplifier and you'll get a capacitive ring down, and then it overloads again. You'll go up here, you can actually see the flat spot up on top where it's actually hit the rail of the response range. Maximum is 50 Gs in this case, so it can't go any higher. The signal rings down again. You can see additional impacts occurring and riding on top of this signal, but until it settles out at 0, all of this stuff in between is absolutely junk. And if I remove the blue signal on top, this is what the remainder of the signals, the other channels, look like. Centered about 0, they look like good vibration data. So this is all usable, but this one channel up here is junk, and I have to disregard it when I'm doing my analysis. So, in summary, think about the goal. What am I trying to accomplish? And once I've figured out what the goal is for my vibration test, then come up with the plan. What tools are you going to need to successfully carry that out? Also, I have the tools. What skills do the personnel require to be able to successfully execute the test? Think about some of the mechanical information that you may need for the analysis part. Before you actually get to the test, it may be prudent to contact some of the OEMs and start getting that information ahead of time. Will you need calibrations for the test that you're conducting? You may have to send out all of your equipment for calibration to have fresh cal sheets before I get to the site to conduct the test, because I'm going to have to provide them on the back end. Think about the visual condition of the machine. Don't blindly follow routes or just take data. Pay attention. Look at the thing while it's running. It's going to help fill in a lot of the blanks. Also, think about the sensor mounting method. Make sure that you're using the appropriate method for the test that you're conducting. And lastly, think about the data. Once you do hit the button and start acquiring data, pay attention to it. Make sure that I'm actually acquiring good data and not acquiring garbage. And with that, I want to thank you for taking the time for the webinar. I hope it's added some value for you. If you have additional questions, please feel free to contact us at ivctechnologies.com. Thank you.
To learn more about condition monitoring of your critical assets, contact us at ivctechnologies.com.